machine learning has so many applications, and mathematics in machine learning is pretty fascinating. I do know that you had another professors talking about machine learnings from computer science point of view, from data science point of view, and they are more professional in those topics. So I'll be talking about math behind it. And I will convince you that we actually do teach some of this math in calculus classes. So you can dive into it pretty fast. So this is the last time I will show you my list, how many applications we're covering every time. And we covered almost all of it. We reached AI, artificial intelligence, machine learning. And I do talk about at some point, not in this class, but at some point, math and music and sports for people who are curious about those things. So just letting you know, in the future, I can talk about that too. Many people confuse the relationships between AI, machine learning, deep learning, data science. So data scientists, they collect the data and analyzing, and then using AI, they train machines to do job for you. So they train machines to do more deeper analysis and give you some better feedback or give some predictions. I mentioned last time something cool like Fibonacci sequence. It was the first class I gave you. And I mentioned because I wanted to convince you that they are cool patterns in anatomy as well, uh, which are basically the repeated patterns and having feedback loops, as you can see, like in some biology and super cool stuff. I mentioned when I was talking about math biology. And then I told you, well, we've seen these things before, repeated patterns and loops. So again, today I will show you how trigonometry saves the day and helps with the approximation of imaging that contains tumors and cancers and so on. Polar coordinates, you are finishing learning that right now, have lots of applications as well. And again, it is used for image recognition and sounds processing as well. So I like to show this dancing tree, which is full of fractals and repetitions. As you can see, each branch gives another branch, which is the copy of the previous branch, but smaller, and then so on and so on and so on. And then I told you that we've seen it before. And that's how I go into image processing. In the past, doctors would increase those images of blood vessels and carefully with images with high resolutions, they will try to see what's wrong and they would have assistance for that. And it's a time-consuming process, but also it's very tedious and have to be done carefully. So you actually know what not to cut, but what needs to have attention. And as you can see, look at those trees that have more little trees, more little trees. Of course, liver and kidneys and lungs, they have these patterns that we've seen in biology and can describe mathematically. So it's a very popular problem called also one of the optimization problems, how to save the tiny vessels at the very edges from lack of oxygen and blood supply that's happening during anesthesia. And quite often liver uh, liver is the one who suffers the most because at the very end the vessels are tiny. So sometimes people have liver failure, but even though they were treated for different reasons, because they were sleeping with medication for way too long. So more pictures of see as you, kidneys also have those cool tree patterns with fractals, basically repetitions and recursions, lungs, heart, blood vessels. So if doctor could look at those pictures carefully and try to recognize the patterns and try to recognize the what is wrong with the pattern. So maybe the vessel got um, damaged or have to have like vessel cleaning or obviously tumor is growing. Why not to train the machine to do the same thing? And you are zooming in more and more, and then you start finding patterns. So fractals on the left again, but biology and anatomy on other pictures. And it is happening. It's happening already for a decade or more that AI is used for early detection of brain tumors using MRI images. Because again, the whole point of AI and machine learning is if we can do it as humans, why not to train machine to do it the way we learn it but in a massive, massive amount, because computer can process millions of images at the same time as we can process 7. So this is exactly how they're trying to do it. How do they know? How doctors know that something is wrong happening here? They do heat maps, or basically colored maps, and then they make conclusions or suggestions that something have to be done. So AI became pretty good at it, and that's kind of what the most fascinating here, that this research was done for so many years that the training becomes better and better. New AI tools accurately detect more than 6 now. I will show you more. I think it will be 16 different cancer types on whole body scans. So prostate and lung cancers, melanoma, lymphoma, head and neck, breasts. As you can see, pre and post treatment. And it's cool that it can detect it earlier than us. Kind of, as you can see, as you can imagine, with cancer, it is pretty important.
Right.
So mathematical neuro-oncology, that is like a whole study, has this name. They're more than just that, but this is official terminology that's used when you look at the collaboration between Mayo Clinic and ASU, and that's where our math students are getting hired to work for Mayo Clinic, which is a top-ranked hospital in the nation, and they are also one of the top in the research done in the nation. And we are lucky to have them in Arizona, in Phoenix, which is not always the case. So to have them in the state, because it's a big research facility. So they build the whole building just to work with ASU, because we're a big research university. And math people are hired there all the time, and our students, our PhD students, being super successful there. So Arizona State University and Mayo Clinic have a strong alliance focused on advancing healthcare through research, education, and innovation, particularly the health future centers and medtech accelerations, which are flagships program of the Mayo Clinic and ASU Alliance for Healthcare. So it's called mathematical oncology, neuro-oncology, exciting interdisciplinary field incorporating applied math, AI, clinical oncology, cancer biology, radiology, pathology, and informatics. Lots of coding, lots of computer science is happening there too. This discipline represents a major paradigm shift in the generation of practical clinical tools to benefit people diagnosed with brain tumors. So as you can see, researchers who never had any degrees in medical fields, researchers like applied mathematicians and computer scientists and data scientists, are working very hard, teaming up together to help predict and diagnose tumors. So Dr. Christine Swanson is a professor and vice chair of research in neurosurgery. She is in charge of this collaboration, or part of the team. She's a professor of cancer research at Mayo Clinic's campus in Phoenix, Arizona. And her research focuses on combining predictive mathematical models and AI with clinical oncology to find how different treatments affect glioma, tumors, and patient outcomes. And there's a whole website about this, and it's very fascinating. Again, I'm all like promoting mathematical applications in your degrees. Anyone who wants to do STEM degree can be part of this, because they need more people to be part of the team, since you don't have to know all of those things listed. You can be part of the team that is good at some of it. And then you help people that have health issues. Another thing is Stanford is bragging about their new mask modeling, which is multi-model transformer with unified mask modeling. So they just recently bragging about it, how fascinating it is that they trained on 50 million medical images of standard pathology slides and more than 1 billion pathology-related texts. As you understand, AI and machine learning works on feeding of millions and millions of images and texts. And then they understand what we as humans, as doctors and medical systems, are looking for. What kind of patterns we're looking for when we want to detect early stages of cancer or have suggestions for the chemotherapies or other treatments. The model outperforms standard models that they had before in ability to predict the prognosis of thousands of people with diverse types of cancer and to identify which people with lung or gastroesophageal cancer are likely to benefit from immunotherapy, and to pinpoint people with melanoma who are most likely to experience a recurrence of the cancer. So some cancers come back. That's the issue. Some of them go away and might never come back, or might come back like in 30 years when you don't care anymore because maybe you're already 85 years old or 90 years old, so it's fine. You kind of don't even want to have treatment anymore because it's more painful than just let it be. But it can predict early. Yeah.
It's awesome, Sarah.
Yes. Any questions? Yeah. So the let's see. Can try to wait. And there were 16 types of cancer. Now they're working on 16. So as you can see, the number increased. The program accurately predicted the disease-specific survival of patients 75% of the time. Before it was 64. This is how it's doing it. It's pretty cool. As an input, it takes different types of images, thousands, millions, and billions of images. So WSI is a whole slide imaging, which is a virtual microscopy. It's a digitalized glass slide, allowing pathologists to view and analyze high-resolution images on computer screen. So that's something that doctors would do manually before. Of course, clinical photography, as you can see, carefully taking pictures of the body parts and the radiomic data, which is quantitative features extracted from medical images, allowing for deeper analysis of tissues characteristics and disease patterns beyond what's visually apparent, potentially aiding in diagnosis, prognosis, and treatment planning. So it also includes quite often heat maps, and that's where you can more carefully see the parts that are heated or colored differently, some kind of patterns that are not supposed to be there, something that might identify disease. So you feed this input into the machine learning. So you have some, it's called feature extraction. You're looking for something, and then that something have some patterns. You tell a computer that we're looking for cellular mitosis. So let's figure out the location and size and shape. Texture and color is important. Now we put it into the machine learning, and machine learning tries to classify those things. Quite often it starts sorting what things are thicker and thinner, like over here in lungs, for example. Those are not lungs, but if you imagine. And then it can do color coding too. And then it can try to do prediction, not only if it is the cancer or not, but also if what type of cancer it is, or if it is normal. So you also can use image patches. So you take some pieces of the image. You see they kind of took this and broke into smaller pieces. That takes you to deep learning, which we're going to talk about in a second. And it also helps with making predictions. So from input to output. This is another picture. The input here is pathologist tumor segmentations. Here they are. This model uses digital images of a bladder tumor tissue sample as an input on the left to predict the risk of the cancer spreading to nearby lymph nodes on the right. So it does this. This is the process. So that's multi-resolution prediction map. Here you go. It's color coding it. It does some pixelized processes here, so we can identify what is happening and which parts are more affected than and which are not. Prediction map. And then also it does image cleaning from the noise. I will talk about in a second. So it increases the resolution by itself. You maybe already can use your smartphone to do it with pictures to clean it, if you remember. So it was done already quite a while ago for the medical goals. As an output, it's supposed to give you some kind of suggestions. For example, in this case, risk is high risk feature localization. And you remember what was the question? The question was not to identify the cancer or not. They already know this is a tumor. What they want to know is the risk of the cancer spreading to other parts, because it's over here. Will it go farther through the vessels or not, through the blood vessels and so on? And they say, yeah, from the patterns, what they see, the AI looked at it and say, yeah, the risk is. Again, AI doesn't give you 100% answers. So that's also important to understand. 75% is really good. And I will also mention a second, how is it happening? I wanted to zoom in for you to check the heat map. As you can see, the red parts indicates more processes or more accumulation of bad cells or whatever we're looking for. And then they are just space in between, and then how it spreads through, also was color coded through yellow parts. So how does it know? How does it know in general what the AI is looking for? And then it all starts with simple questions. Can AI tell a difference between pictures? Can it also identify what it's looking at, for example, as a creature, as the image of flowers? And it all starts with those silly questions of distinguishing between animals. In fact, the easiest animals it was to teach was to identify penguins because the most of them are black and white and they have the same size. So it was funny. I was reading about somewhere. But how about cats and dogs? Like, how do you would explain to AI the difference between a cat and a dog? Sometimes I try to imagine it's like explaining to a blind person what is the difference between those two animals. Like, as you can see, sometimes they even have the same size. They have two ears and they have four legs and a tail. So, and they usually have fluffy. So, how would you explain it? What is AI looking at? Well, the machine learning process has lots of iterations. That's what they're showing in between. They have layers and layers of iterations. So it's not like it's looking at it and then tells you, I think it's cat. No, it's going back and forth again and again and again, looking for some kind of features that we trained AI to look for. The coloring, the viscous, the shape of the hat, the eyes color, and so on. We feed data into the model and measure its accuracy through the objective function. You heard this phrase objective function before in optimization models. It's basically the goal. Remember, we were minimizing and maximizing objective function. So we, with the help of optimization algorithms, just like we did with optimization problems, we vary the model's parameters, weights, and biases until we reach the desired output. So we will be changing some of these layers weights. And weights means how much we want to make one or more of these paths more important. And biases. And biases here, they explain it as are we more biased towards smaller tail or larger tail for the cat? Are we more biases for the smaller size or larger size for the cat? And the more we tweak those things, the more we will be able to help the AI to identify that it is indeed a cat. This includes the whole training stage. So it has to go back and forth to be trained. Here you go. So we're feeding the computer this picture of the cat. And it's called a deep neural network because as you can see, it looks like brain with a neurology signaling happening back and forth. It consists of a hierarchy of layers, so sequence of layers. Each layer transforms the input data into more abstract representations. So, for example, edge, at the edge, it has a nose, and that's a face. And another edge, there's ears, and ears have sizes. The output layer combines at the end all of those features, which is like sub images of the original image, to make a prediction that, oh, I think it is indeed a cat. This is an increased version. So it's very cool that it does break it into parts, and each part is responsible for some kind of different feature, eye colors and ears and so on. And that's where we start teaching students about forward and back propagations, which is basically a part of AI image processing. Forward propagation is the first part we teach, is the process of pushing inputs through those networks, right? The net we just saw. At the end of each point, I think it's supposed to be point, we compare the obtained outputs to the targets to form the errors. In this case, we know what we want. We knew it was supposed to be a cat, so we know the answer. We compare the output with what we want and subtract the results on each layers to see what the errors happen, what kind of errors happened in the process. And then we convert it to backpropagation. We reverse the whole process and adjust the weights, knowing what the errors the AI made on the way. Where did it mess up? We adjust these weights and biases to minimize those errors, right? So to minimize the loss, and that's why the loss is the error, as always. Backpropagation is a short for backward propagation of errors. It's an optimization algorithm used to improve the accuracy of AI neural networks. It is an essential component of the gradient descent optimization process. So we learned optimization problems in Calculus 1. We learned derivatives, and in Calculus 3, we're going to teach you gradient descent, which is used in almost every application in the world. It's a very important mathematical strategy for the optimizations and other things. This is how the neural network looks like. So in this case, it has 4 layers, which is a simple case. Of course, it has hundreds of more layers in general. Here's the input layer. The neural network is one with 4 inputs, 4 layers, 4 neurons in the hidden layers, and 1 output. Input has 4, and then 4 layers, 4 neurons, and in the hidden layers, and the output, the answer S. Each array represents mathematical transformation. So, and the arrows will have weights. Actually, W usually stands for weights. And the arrows will tell us the color of the eyes should be red. Okay, but it's not red. Going to this level. Oh, the ears should be bigger. Let's keep going after that. So X, as always, is our input. That's not surprising. As always, it's kind of we're trying to recreate the functions that we learn in mathematics. And it has an equations. So some are A's, and there's lots of different A's for the input. So let's put it in the form of the list, right? It's like Excel file list, but it's a matrix. So I'm not sure if you know what matrices are. Hopefully you do. And that's when you will not be surprised that's where we use matrices so much, because it's just a convenient and helpful way to organize information. And then we know how to work with them. We know how to multiply matrices, add them together, and do some upper level math to analyze it and get into the answer, solutions S. So the weights are collected here. This is just W1, but there will be more, of course. Let's collect them as well into many parts of the matrix. B is also collected as B1, B2, and so on, and it keeps going. So we're collecting them into the matrices. So we take W's, multiply by X, and add the B's, and knowing the properties of the matrices, we know how to do it. We multiply components by components, add them together row by columns. So that's what we teach when we introduce matrices. And that's how we get a new function. Z as the answer. So again, input as X, output as S. S is now has a relationship with W, the weights. The weights got multiplied. Each different weight got multiplied by each different input of X's. But X's are inputs called A's. So the answer became W and A. And this is of one of the iterations, right? This is a cool animation of how you can see through the matrices representation. I don't have to make you struggle with understanding lots of details here. But as you can see, how it's multiplying things and add them and collect them into the matrix representations layer by layer. First, there are a few layers, then it gets into deeper layers of neural network and the matrices increase. Delta W's are the weights and how fast they're changing, or the changes of the weights, adjustments of the weights for the minimizing the error. At the end, it gives you different results, and they are percentages. So, the computer is 42% certain that it is cancer. 34% it thinks it's not. 90% not sure. 20% it thinks it's another cancer. So it's just an example of what it can be. On the way, we're collecting the mistakes, because mistakes will happen. the errors will be made. Before backpropagation is used, before we reverse the process, the weights will be off. So we want to find out where and why the computer messed up and why it led to the error. Why does it have 100% accuracy? Why I cannot say that it's cancer with 100% accuracy? Because there will always some kind of errors on the way. So let's collect them. Let's not forget them and throw them away. This is important information. We're going to call the cost function. So the values of S can then be used for a cost function. S is an output. Remember, it's a result. Result tells us where the computer messed up on the way. C is a cost function, calculates the average deviation. Deviation means difference, right? It's a statistical term, how much it is different from what we need on averages. Deviation of the neural network's result from the expected result, Y. So Y is what we know. It should be a cat. S is the prediction, and say you computed it well. It's a cat with 63% accuracy. Why it's 63? Where the error was collected, not like at the very end. It was collected on every step of the neural network process. So we're going to collect those errors and find the differences. It literally takes the difference or the deviation and the average of it with what we wanted with Y. On each step with A, it's a classic way to take absolute values, and we're going to teach you what this is, a norm in calculus 3 class. Square them, sum together all those errors on each way when the computer messed up identifying the color of the ear of the cat or the size, or maybe pixels were not good enough and the eyes and so on. And we're taking the average, and there's like a classic way to average up those kind of functions. Here you go. Some more formulas. I'm not going to dive into that. I just wanted to show you that we did learn lots of stuff already. So the goal is to reduce the cost function. We want to reduce the error of what the neural network did to make the predictions better, to make it so reliable that doctors can perform surgeries based on those predictions. And doctors don't want to perform surgeries unless they're sure, right? It's a big risk for the patients. Directional derivatives will be taught in calculus 3, vector calculus. They're derivatives of the cost function with respect to the weights. So we're going to find out how the cost function will change with respect to different weights, right? And that's when we're doing the backpropagation, we'll adjust the weights to make the cost function smaller. The algorithm that computes the gradient and the desired change of these weights and biases for a single training example is called backpropagation. Gradient is also taught in calculus 3 class. I will talk about it in a second as well. So some formulas, as you can see, lots of derivatives, series, we just learned them, right? The summations. Delta means little change. We also know that from the definition of the derivatives. Small change, original plus small change. A negative times derivative means negative derivatives means something is decreasing, right? And these partial derivatives, we already covered them in previous classes. Well, my talks, right? They are derivative with respect to something specific. So we actually did see these things before. Well, automation using convolutional neural network is also very popular for image processing. It's called pattern recognition. And that's how we kind of imagine how we see things. How do we know that in front of us is a cat? We know the patterns. Our brain learns lots of patterns through all the years of your life to recognize that this animal indeed is cat. Starting from being a small kid when you point out the animal and say fluffy, and then your parent says that is a cat. And you've seen so many cats that now you have a pattern recognition system in your brain. So what does computer do for us? It's can handle blurring, sharpening, denoising, and I will talk about that as well. Denoising means making the picture cleaner, taking out those extra dots and lights we don't need to make sure we're only looking at what we want to look. It's also using Gaussian kernel, which is normal bell curve distribution. That's why lots of probability and statistics is involved. You remember the bell shape in normal distribution? And here's some formulas. And that is also some things that's happening with automation. The coding, of course, lots of coding is happening, and we have the cycle. Remember I told you that there are repetitive patterns happening and recursions in the algorithms. In this case, they're showing gradient descent. So they optimizing weights and biases here by subtracting some changes. You see the derivative of the cost function with respect to the weights. So they're subtracting it until it's good enough. So we're minimizing the errors. For example, I wanted to show you, I always show it to students in even calculus 1 class, that we use chain rule. I usually ask in my classes, okay, if we have a derivative of, if we have a function called sine x cubed, we want to differentiate it. The derivative of sine x cubed is cosine x cubed, correct? Well, something is missing. We also need to multiply by the derivative of the function inside, right? And that's what was important part of the chain rule. There's a chain reaction happening. There's a function inside of sine. We need to differentiate it as well after differentiating sine itself. The same thing is happening here, but in upper dimensions. And multidimensional calculus is calculus 3. So we're teaching you this, and this is the heart of the machine learning, and that it is using chain rule. Backpropagation uses chain rule. As you can see, derivative of the function will be derivative of the outside function times the derivative of the function inside. And then it's happening many, many, many times. Again and again and again. And this is a number of layers that we're using in neurons layers. And we give the program code. We have L-1 layer. Please stop when you're done, blah, blah, blah. Here it is. Simple cases to our to general cases. We add up all the weights. This is a cost function. You see, we're adding all the weights on the cost functions to accumulate the errors. And then we want to adjust the machine learning process to make sure it is better, it is more accurate. And the final value happens. So for the backpropagation in the neural network, we can determine the slopes of the costs. The cost relative to the weights at the given time. Remember what slope means? Like how fast something is increasing or decreasing, right? How fast something is changing. So that is also called local gradient or global gradient. That is important because we want to know at every single step why the cost suddenly increased and by how much. In the step 705, the cost function was, say, 3%. And suddenly it increased to 7.5. Why? What happened there? Did the computer struggle to recognize ear's shape, or it was the color of the eye? So that's why we want to find those derivatives to figure out what happened. And it's called gradient descent, which we teach in multivariable calculus, calculus 3. And we are looking for the best possible weights for W and B, which is weights and biases, right? So, and we tell them, and it's when you're done. It's a basically algorithm for optimization of weights and biases here. Gradient descent is amazing application. I will show you in the next slide. Okay, again, showing you one of the last times the complicated math before I go to cool images again. We receive a new observation. We call it X, right, as always. We want Y star. We know what we want, and that's not what we're going to get. The computer will not give us Y star. That's the goal, but it will give us Y with the error on it, right? So it's hopefully, says us the cat, with like 97% accuracy, but maybe it will be 75% accuracy. Is it good enough? That's up to us to decide. We feed it forward. For each unit, we have layers. You see the layers that happen. Oh, X's are on the right, this time. Then we collect the errors. So we know what we want, which is Y star, but we got Y. We take a difference to collect what errors are. And now we're sending it back. And we do backpropagation, just like we did here. We feed it forward. We got the percentage for cat. Now we feed it. Now we go back to collect the errors on each layer and adjust the weights to help the algorithm to have a better answer. Again, this is how it works. We take derivative of the result, and we want to, derivative tells us how fast something is changing, right? So it's basically answers the question, should it be higher or lower? What is happening with the error? Then we figuring out, you see this bell shape again, how changing the weights will change the result. Is it too high or too low? We collect all those errors together. That's the summation sum. The summation sign is for. And then we see how each layer affects the result. We're computing the errors, adding them together. changing the weights, and then we updating the weights and go back into this process. And you see those notations, that often means matrices, which we saw before. So it's basically an optimization model, right? We're looking for global minimums here. We want to minimize the cost function, and we just learned about it in the previous classes. Corresponding derivatives, we call them partial derivatives, multiplied by learning rates and subtracted from W and B, weights and biases. Eventually, that leads us that weights and biases become the local minimum values in the cost functions. And that's what we want, local minimums and global minimums for the cost functions. That leads to the least possible error with the given data set. So it's learning, it's learning and getting better. We want to have the least possible error with weights and biases introduced. And this is a 3D version of global and local minimums. We're also going to teach you that in Calculus 3, multivariable calculus. We're basically taking all of that and putting it into 3D. So figure out local minimums and global minimums on this heat map. So this is a cool animation of the gradient descent of the functions given in 3D, z equals 10x squared plus y squared. And then gradient descent means using derivatives on every step. We're trying to figure out how to get to the minimum as fast as possible based on where you are at the moment. That's like the easiest way to explain it without going deeper into the ideas. And on every step, we take derivatives. So this is a cool animation of what gradient descent can look like depending on different starting points. And you see there's a local minimum introduced and global minimum introduced. And that's also what the machine learning is doing, is going through many, many local minimums and trying to figure out the best possible solution with the most minimum cost function using the gradient descent. Descent is exactly what it means, like descending down. And gradient also means gradation change of the heights, which is basically derivative. So here you go. Like, how do you explain to a computer to differentiate some classical objects? So cats and dogs are already complicated, but even going to the basics, the difference between the donut and this object which we use to save people when they're drowning in the water. So how do we know the difference, right? If we see those two pictures, we have some kind of understanding that, oh, this has like little things on top. Probably it is a food because it's like leaking. It's probably a cream. So how do we know? Like, why do we know it's a donut? And now try to explain it to a computer. Let's go deeper into that. The computer takes a picture of an animal. It's not even moving, right? It's here, it's fixed. It takes, and then we tell them, okay, check the shape of the eyes, shape of the nose. Does it have whiskers? How big they are? What's the ears? What's the size? And then it's put in different layers, uses different programs to give you the result. And hopefully it's the correct result. Because again, how would you explain difference to a blind person, difference between cat and dog? It is pretty complicated. And somehow we do it so well as humans. So we train the computer and hopefully it will give us a confident result after feeding thousands and thousands and thousands of pictures of cats and dogs to give some kind of understanding of where is the difference. But again, even dogs can be as small as cats and cats can be big as dogs. So it is a complicated issue to know the difference. As you can see, not all dogs or cats look straight in the camera. They sometimes are tilted and sometimes they turn to the sides. Sometimes the ears are up and sometimes ears are down. So how do we, and the coloring is also crazy. It can go from all kind of different colors to different patterns and so on. This is the basic sum of the methods of how machine learning is figuring out what is happening when it looks at a picture. One of the methods is clustering. It can try to collect the pictures of cats and dogs, for example, by colors. All white cats together, all white dogs together. Maybe by shapes. So colors were here, green, orange, blue, gray. Maybe by shapes, like all the small cats are here, all the big, so all the small animals are here on the pictures, all the bigger are here, and dogs tend to be bigger. So that is pretty helpful. I can see that. Oh, that's what size. Bigger and more or less the same size. That will help when it comes to recognition of distinguishing dog versus cat. Maybe by shape. Does it have a tail? What kind of length of the body it has? Is this when it's sitting, is it tall or not? What kind of paws it has? So different ways to cluster images. Well, from this interesting layering happening, we can have a more complicated issue. What if even we are not sure? Is it a cat or a dog? Like, look at this. It's looking at you straight. We don't even know what's happening here. It's in a basket full of laundry, sleeping. If you look at it and you'll be asked, oh, hey, friend, is it cat or dog? Can you have 100% certainty without approaching it and touching it? Because that's all you have. Like, you're just staring at it. So this is what's happening. It's feeding this picture and it has inner layers. It takes it and distributes into some clusters. How big it is? It seems like to be small because we know the size of baskets. Its color is brown. It's going to be a different layer. So it activates different neurons to kind of consider different options. And the very end, hopefully, it will recognize that it is not a cat. It will have two answers. Cat, it is a cat and it is a dog, but it will have higher percentage, hopefully, that it is indeed a dog. Why? Because you see all those neural networks, most of them are collecting more heavily towards the dogs. That's called deep neural network. How about handwriting? Some of you guys have horrible handwriting. We as teachers know. We grade your answers, proofs of theorems and, optimization problems. And sometimes I don't understand why it's so hard to write down a beautiful number 3. So nowadays, computer is really good in identifying the handwriting. And again, look how many iterations it's doing it. Different colors means different weights. And it's going through inner layers of the neural network. And then it gives me several results. As you can see at the very end, it was kind of considering that it was 3, 7, and 8. Specifically 8, it was like maybe it's not written well 8. And that's why it's color-coded it based on the accuracy. 3 is the most confident one, and more layers of the neural network pointed at 3. This one is even worse. Like, what is that? Is it 5? Is it 7? Is it 3? So it has more light, white answers at the end because it is harder to understand this time. So it thinks like it's maybe 2. It does look like a 2. It may be 5, and it may be like 9. 6 is also close to it. So it goes back and forth. You see, it sends the results back to the beginning to adjust the weights. And at the beginning, it has some kind of weights that immediately said, okay, it's definitely not 0. It's not circular enough for that. Definitely not 1. It has too many wiggling things. So it's keep going. What if it's moving? What if whatever AI is trying to identify is a moving video? So that's basically is the highest level of identification. As you know, we have cameras on the streets that can identify you as a human that's moving and so on. As you can see, it's always have pretty high accuracy when it comes to human in this specific video. The person has like 97, 98% accuracy when it's moving. It has like changing accuracy for the couch. It thinks it's like 30% couch, but sometimes 50 or higher. Somehow it's depending on the movement. And the dog is sometimes covered by the guitar, and sometimes it's not. So when the dog is covered by the guitar, the accuracy is only 33%. But when a dog comes out, it goes up to 93. So it's pretty cool how on every step, it's keep adjusting the results based on the new information fed to the system. When the dog is coming out of the guitar, the computer sees the face and now can add this to the AI network. Well, we already have had all this working in our autonomous cars. So there's whole research done on that, and it's pretty fascinating as well. For example, the Vanderbilt test that was one of the biggest tests in the whole world, and definitely the biggest test done in America. They did wanted to use mathematics and AI to improve traffic flow and reduce energy consumption The team conducted experiments in Nashville, August 6, 2021. And my friend, as a scientist, was one of the leading researchers there. That's why I like talking about. So they use mathematical modeling and deep reinforcement learning and controlled autonomous cars. They're called COVs, basically automatic cars. The experimental design consists of 4 automatic cars and 7 manually driven cars. They injected those cars into the highway. And by injected, it means they took police 4 or 5 in the morning. Police would take those cars and surround them and put them into the highway and then leave them alone there because they want them to stuck in heavy traffic in Nashville to collect the data. 11 cars had sensors everywhere to monitor and collect data. What kind of data they needed? Cars velocity, acceleration, space, leading cars velocity, cars behind of the cars velocity, and other stuff. This is the team. They woke up 4 in the morning. They were trained. Police was trained what to do. Drivers were trained what to do. And then some of these people are mathematicians. These are the collaborations between many companies and governments. And this is my friend, Janie Gong. She was one of the leading mathematical researchers there. She's actually a graduate PhD student from our School of Mathematical Statistical Sciences at ASU. And now she's working as a professor, assistant professor in the Amherst College, very respectful with lots of grants on these topics and other topics too. So she works on a team that wants to reduce traffic. And the study says that to reduce traffic, we need at least few automatic cars on highways because they tend to do well. And then other cars try to imitate other cars with humans in them tend to imitate good behaviors. So it should be doing fine. And yet it's not doing perfect. As you can see, there's lots of ghosts happening. Ghosts are the things that are not there, but computer is detecting them in blue. Look at the blue dots sometimes showing up, blue and green, both. But there's nothing happening. There's a big truck. Yes, it recognizes it pretty well. There's the green car in front and yellow passing by on the left. It recognizes it pretty well. And what are those dots? What is this? What is the computer seeing around? So those are basically errors and mistakes. And they're trying to optimize those objects to make sure there's less and less mistakes. But for that, you need to feed more and more data to the computer. This is how it's done. This is the process. We have a sequence of events occurring during the driving scene. Trees, someone crosses the street, the colors, the lights, and the face. That's how we see it as humans. The driver has subjective, not objective, right? Belief about the probability of something occurring, the event. Like how highly likely that this kid playing on the green side will run into you? How high likely that the tree will fall on you right now? Or the car will merge into you? From that, we perceive risks used in the risk threshold theory, and we start plotting all of this mathematically. It's a cost assigned to events occurring in a driving scene. Here's the cost function. Here's the driving scene in 3D. Then we build driver's risk field. Remember, we all talked about risks and cost functions in the previous. We multiply by all of that. And now we add all of this together to collect quantified risks with the as well series representations, right? And we have proposed perceived risk metrics. So the government is keep a close eye on those things, which is for example, SIA, the international is the world's leading authority in mobility standards development. So they are the one who design patterns, standards, and certifications for safety, productivity, dependability, and efficiency of the cars. And they had levels, no automation at all. That's what we all had. Some automations, so anti-lock brakes, dynamic cruise controls, right? That was in cars already for a while. Level 2 is partial automation, which is steering and acceleration, deceleration. It can do it for you. Conditional automations is level 3. All aspects of dynamic driving tasks will with expectation that human will respond to when it will be requested to intervene. So you still have to hold the wheel and stuff. High automation. All aspects of dynamic driving task will be done by the computer, even if human does not respond to requests to take part of it. So it's completely automatic car with no driver. We have that in Tempe, in Phoenix, automatic cars driving with no driver, and they're taxi cars. So they do everything. The person who is in the backseat does not do anything. That is level 5. So some partial automation is to detect something in front and to stop ahead of time without hitting that object, either that is a car, a wall, or a pedestrian. If it's just moving forward, it was kind of not as hard to model it through linear equations. This is moving forward. Yes, the object passed by. We have several solutions to this issue. The car stops, brakes, that's a blue option. The car doesn't brake, that's a yellow option, and hits the object. Or the car brakes, and hits the object and moves on. Or the car brakes and stops on time. Well, let's call it one-dimensional word model. So that's a simple model with second-order linear differential equations. Differential equations are used because there are lots of derivatives here. What is happening? What is changing? Now imagine it's not linear. How about people just start getting into car crash and everything starts swirling to the left, to the right? That involves rotations. That's called they use non-holonomic system of equations, which is basically classical mechanics. If you like physics, I talked about it in my previous talk about NASA and stuff. And the moment it includes rotations in 3D, it becomes more complicated. Now everything changes, not just the nose is rotating, but the wheels and the tail. And you have to take this into account using lots of trigonometry. Here you go. It's called Lagrange equation of motion for non-holonomic systems. Not only one piece is rotating, but other pieces that connected to it are rotating as well. And you have to predict where it's going to help the car to stop properly, not to hit more things. So, and also to code what response should be in the first place. Imagine the automatic car happens to be on the ice. Here you go. This is my friend's research, Janie Gong's research. That is in Amherst College right now. As you can see, you might be surprised that they do have theorems and proofs and definitions when they model automatic cars. It's not just computer science, machine learning. It has a lot of math in it. So there are convergence theorems. There are limits. Let me actually zoom in here. There are limits. We learn them in calculus 1. Convergence happening, calculus 2. Double integrals, we teach them in calculus 3. Gradients, we teach them. Partial derivatives, we teach them in calculus 3. And so on. So all of this series, of course, and summations, right? Calculus 2. All of this is done to teach the machines to drive. So in Arizona, we do have Waymos. They drive automatically, and they were allowed by the law. I'll skip that, but I have a cool slide. Sorted by years of how our government decided to allow or approve different levels of tests for the automatic cars to be on the streets. So in 2015, they approved some testing. Then, I moved to Arizona in 2017. And I saw the Uber automatic cars driving in neighborhoods just to learn. They did not do anything yet, no passengers. Then they will learn to deliver things with no passengers. And then a person got killed. And we became well known in the whole world as having a first death case in the done by it's a first pedestrian fatality involved self-driving car, first recorded case. It happened when I was there. It happened in my neighborhood exactly a year after I moved into Arizona, and we know where it happens. I walk there all the time. So after a collision that occurred late in the evening on March 18, this is the lady that unfortunately got killed. Hasberg was pushing a bicycle across a 4-lane road in Tempe, Arizona, when she was struck by an Uber test car. It was just testing the car, but it got hit. It was operating in self-drive mode with a human safety there in the driving seat. Prosecutors ruled that Uber is not criminally responsible for the crash. And that's a good ethical question. So the person got killed. Who will answer for that? Who is responsible for this death of a human, right? Is it the car? Is it the company? Is it the people who coded it? Is it the computer scientist students like you who coded something? Is it a data scientist? Is it a mathematician? Who is that? So they decided that the Uber company is not responsible, and they blamed the backup driver who did not respond fast enough to stop the car. The driver did not pay attention enough. The driver pled guilty and was sentenced to 3 years probation. Uber was completely eliminated from the streets after that. They left to another state. So, but this case definitely magnified the importance of collision avoidance system. It would be nice if the car would just stop by itself. It didn't. It was supposed to recognize the pedestrian crossing the street. It was dark, and it didn't recognize it, and it did not stop and hit the pedestrian on the 39 miles per hour speed, which is a deadly speed. Various technologies and sensors that are used now include radar and lasers for all weathers and cameras that employs image recognition to detect what is happening around the car at all times and to stop the car from crashing into another car. The sensors can detect fixed dangers such as approaching stop signs through a location database, pedestrians crossing the street as well. Well, it is a complicated process. This is a Waymo. I actually took it from the Waymo website. They keep updating the progress. As you can see, this Waymo is driving in San Francisco, which is super busy. And it can detect humans crossing, someone is hesitant and standing, not crossing, some car just passed by. It can detect it as well, and it needs to keep going. So now it's time to keep going and slowly keep crossing, and it detects all of those humans, the heavy traffic people coming back from some event in the evening, and this person got way too close, but it saw the person. So another video of going through the streets, it knows there's a car in front, then the passenger jumps in front of the automatic cars. Don't do that. Don't jump in front of cars in general, but specifically in front of automatic cars. You don't know if they're good enough to stop. Luckily, it recognizes it, and even it's following the car, but then the pedestrian jumps in front of it and it stops, and the cars keep disappearing in the future. Luckily, it's keep going safely after that. This is the video recorded. Image recognition, as you remember with cats and dogs and whiskers and eyes, figures out, okay, there's a car here, there's another car here. It's pedestrian, something unknown. You see, so it's not sure what is that, and something unknown here too. And this is how it looks forward. And it sorts things. Remember, it can sort by like sizes and colors. It sorts things by the most important objects, for example. Size size and shapes explains it if it's a car. If it's a square kind of object, big objects, usually a truck or a car. If it's a thin object passing by, it's probably human. Vision detection, radar detection, and so on. This is the view from the top. So it's interesting that there was a carriage with horses on the street, and it was very hard for the AI to figure out what was it, because the size kind of recognized it as a car carriage with the horses, right? But then it was very slow, so it thought maybe it's a person walking, but a big person. But then it also was kind of having wheels, so it was thought maybe it's a truck. But it was too slow for a truck, and it was not a square. So very interesting that there's still objects that the car does not know what to do about. And I always also wanted to mention that we use machine learning in image processing and recognition. I mentioned that. And from image, I showed you the videos also. So videos, of course, we're jumping to the upper dimensions from image to video recognition. It's also used for writing recognition. We saw numbers, right? Speech recognition. Can I talk to something and it will recognize what I'm saying? Yes, it can. Patterns recognitions are used quite often. For example, spam filtering in your Gmail or your Facebook account or Twitter account can have some patterns recognizing of what you like and gives you more things to read about that. Voice recognition was there for a while. Siri, Alexa, Google Assistant. Image and sound denoising. And I want to briefly mention that. What does it mean to denoise or to clean the image? Well, the hard parts were, can it write after I talk to it, right? So it recognizes my speech and it writes, called type, talk to type. People using all the time. Image to write. If it sees the image, can it write and explains to me what is happening? So describe what you see. Say I'm a blind person, but AI is showing an image of an apple. Can it write? Wait, if I'm a blind person, I will not read. So I'm a deaf. Well, anyway, I guess I just realized I'm a deaf person, right? Can it read to me what it shows on TV? Writing to image is one of the hardest ones. If it reads the book, can it create the image of what it just read? Create a picture from description. So we'll mention that. and pattern recognitions like spam filtering again and other things. Voice recognition again. So if I talk, can it write it down? It goes through the natural language processing. It recognizes your language, your accent. So I have a Russian Ukrainian accent, right? And then it tries to figure out how to write it down. So it's called text to speech. Denoising is happening here, filtering, and is often used to denoise things, which means you see it's not a clear picture. It recognizes all the noise and makes it clear. Again, Fourier transforms are happening. I already mentioned to you yesterday, right? So it actually helps a lot with denoising both images and sounds. So if it's some music, for example, but it's someone coughed in the background and there was like a clock. I have aquarium water right now. I don't know if you can hear it or not. On the right, the aquarium is running. Those are noises. The noises are small, tiny sounds, so they have slow frequencies. Why not to detect them and then just cancel them and leave only the one we need, which is the music or me speaking. So these are something with high frequencies. And again, it's used trigonometry. As you can see, those are sines and cosines, and they connect together these things and cancel the one with low frequencies. So last three pictures for you. It still messes up. We try to text or write down to AI, can you please draw a picture or create a picture or find a picture? There's two baseballs to the left and three tennis balls to the right. And it gives me this. Well, first of all, it's not even correct numbering. I wanted two to the left and three to the right. Then there's like some color bleeding is happening. Why there's a yellow outside of the ball? Feature merging. Why there's something happening in the background and it's merging into each other. Incorrect spatial relations. It's not the correct size and so on. So like, what is happening? Why it's not correct? I found the pathways autoregressive text to image models. It's called party. So they're showing examples of the code for a model called party. Okay, a plate that has no bananas on it and a glass with no orange juice in it. It struggles to do that too because it doesn't understand no idea. Like, what does it mean to have absence of things? So it did exactly the opposite. It's a plate full of bananas and the glass of the juice, a glass of orange juice. And also why the glass is standing on the plate. That's not really clear, but that's interesting. How do you explain? What do I see? I see a plate with no bananas and a glass with no orange juice. Can you draw that? Like, what will you draw? A squirrel gives an apple to a bird. Okay, well, that one is also interesting. First of all, this is the millions or billions of tries or image processing, or basically those stages, right? So why the two squirrels, no birds, and they both holding some apples? Then it's trying to do something, but completely messed up. It's fine, but there's at least an apple and a square. Okay, now it gets much better with 3 billions jumping from 750 millions tries. It has indeed a square holding an apple and then a bird. Bird looks kind of weird though. And finally, the last result looks the best. But it's interesting that it has to decide what bird it is, what color of the bird, what the size of the bird. Why it's not a turkey, for example, right? Or a pigeon, or an eagle. What type of the square it is? There's so many of them. What color of it? And also an apple. What color of apple it is? What size of it, right? So it has to make all of those decisions, which you, as a requesting person, did not specify. And we all know those classic struggles AI has with the spaghetti. Like there's something about spaghetti that makes it super confused that it doesn't understand how we eat spaghetti and what is that. So every time you request someone put any name, eat a spaghetti, the person is fine. Holding something is fine. The plate of spaghetti is usually fine. But like the eating process is super confusing. So with all the technology, they still mess up. It is what it is. That's my final conclusion here. It's keep learning, and that's why it's called machine learning. It's keep learning and it's getting better. So that's my last point here. I, as always, try to tell you that you can make it work better, right? When you go to grad school and you learn all of those things, and no matter what your interests are right now, be open-minded because you will never know if you end up to be a mathematician learning, studying, helping in medical system, like computer science, helping with tumors, or maybe a data scientist helping with automatic cars, or NASA shooting the objects into the asteroids. Questions? Questions, ideas, comments. What do you think about any of this? What was your favorite part? And have you heard any of this before? Like, what do you think about any of this?